Okay, in this lesson we take that perpendicular bisector concept from the last lesson and bring it to what's called a circumscribed circle. And circum means to go around, so when we talk about circumscribed, we're talking about going around an object. If you later see the word inscribed, it means we are touching the object from the inside part. So circum means going around it, so you'll see a surrounding sort of thing going on here. So in exercise 1, which of the following shows a circle circumscribed about a triangle? So that means that it goes around the outer edge of the triangle. The one that does that is number 2. Number 3 is an example of that inscribed concept I was just talking about. 1 and 4 are neither, because you can see that some vertices touch, some do not, and some are inside, some are outside. Number 2 is the circumscribed one, though. Alright, so the circumcircle, which is the circle that goes around a polygon, is closely related to that perpendicular bisector concept that we talked about in the last lesson. So the steps here, first, there's a lot going on in this diagram, I realize that, but what's going on here first off is the perpendicular bisectors of sides AB and BC were constructed. So here's side AB at the bottom of the triangle. You make your football construction there. So we have these two arcs here. You can pause the video to do that, get those drawn in. Then we go over to segment BC, and again you can pause it to do this one. So we have our football running this way. And what you should have is both bisector lines connected as well. So this vertical line I'm pointing to here connects the intersection of those two arcs, and this one here connects the intersection of its arcs. You do those constructions lightly. It'll be a little bit easier to see the parts. You might even choose to use a colored pencil to differentiate them. But those two perpendicular bisectors are all we end up needing. And as you can see, the reason is point D, this intersection of the bisectors, point D falls on this vertical bisector for AB, and so that means that point D is equidistant to both A and B. Just by definition of a perpendicular bisector, remember it collects all the points that are equidistant from the endpoints. And point D here is also on the bisector of BC. So that means that it is also equidistant from the endpoints of that segment. So it turns out that point D is equidistant from all three endpoints, and therefore it is true that AD and BD and CD are all the same distance. So that becomes the center of the circumcircle. They're all essentially playing the role of the radius. So if I put my compass on point D and connect it to either A or B or C, I should be able to draw a circle that touches all 3 points. Now sometimes this works out perfectly and your circle touches all 3 points perfectly, and sometimes it just narrowly misses 1 or 2 of them. It just depends on how accurately you make that intersection point. So don't sweat it if it's a little bit off. You want to just get as close as you can to it. You notice that there's only 2 bisectors drawn here. The third one would also run through the same point, so it's not necessary to do 3. We just need to find out where 2 of them intersect. So you can stop there and go to your circle as soon as the 2 bisectors are drawn. Alright, on the next page, the fact that all 3 perpendicular bisectors intersect at the same point, that's a phenomenon called concurrence. When 2 points meet at the same place, they are known as concurrent. So 2 different bisectors meeting at the same point form what's called the circumcenter. Now that word should kind of fall in nicely to what we've been talking about. If it's a circumscribed circumcircle, it has a circumcenter. So that's what point M is called. Now, when I construct this, I took segment EF and bisected it with our standard construction and ran that through here, and did the same thing with FG and ran that through here. Point M, the intersection of the 2 points of the 2 bisectors, was not inside the circle, inside the triangle like it was on the previous page. Let me just go back to that for a second. On the previous page, point D was on the inside of the triangle. On this one, point M is on the outside of the triangle. However, to make the circumcircle, I still need to connect my metal point on M to a pencil point on any of the other 3 points, and then go around the triangle, and it makes a rather large circumcircle, but it does the same thing. So why is it that the circumcenter falls outside the circle in this case, where it was inside before? It has to do with the kind of triangle we're looking at here. Whenever we have an obtuse angle, that circumcenter will be outside the triangle. And if it's an acute triangle, all three angles are acute, it'll be on the inside. So that's the reason. If it's an obtuse triangle, we're going to be on the outside. All right, and now we have a right triangle. And you can see that this circumcenter falls on the hypotenuse. So let's just take a quick look at why that is. First off, and again, you can pause the video to do these constructions, but it says to construct the perpendicular bisector of the hypotenuse. So if I do that first, you can see right here, these arcs here are making my bisector run through the hypotenuse. And then if I label that midpoint as point C and draw a circle right then and there, where the radius is from C out to R or C out to Q, either one of those, since it's a midpoint, I can use either one of them. Normally, that's not enough. I need a second line to be sure that it's going to hit all 3 points. But in a right triangle, it does end up hitting the third point. And you should notice that if you try it yourself, that when you connect R and Q with a circle, you end up going through P as well. And the reason for that is for right triangles, the circumcenter will fall on the hypotenuse itself. It'll be on the midpoint. So acute triangles, the circumcenter is on the inside. Obtuse triangles, the circumcenter is on the outside. Right triangles, the circumcenter is on the hypotenuse itself. All right, and so draw a line segment CP. We bring that back here. Explain why CPQ must be isosceles. Well, we're looking at this triangle in here. Remember, isosceles triangles have 2 equal sides. If we are taking from the circumcenter out to P and from the circumcenter out to Q, we're looking at the same circle. So that's 2 different instances of the radius of that same circle. Therefore, they have to be the same length, and we have our isosceles triangle.